In this video, we'll try to go deeper into the basic electrical components that we are familiar with, and those are the resistor, the inductor, and the capacitor. We'll look at how they are constructed, understand how they really work, and check out the variations that are out there for us to use. We'll first take a look at resistors. Resistors are electrical components that basically restrict the amount of current passing through a wire. In essence, all materials have electrical resistance, but resistors are designed to have a very specific resistance to current. The problem is, once that is manufactured, you can no longer change its resistance. Thus, if you need a specific current or power for your device, you have to find the right resistance that will allow your device to run properly. You can then essentially classify resistors as a type of conductor with very specific conductivity. Resistors are also differentiated from semiconductors since you can control the amount of current through semiconducting components without changing the device. The most common material used in resistors is carbon, but you can also use metal film type. Carbon-based resistors are easiest to manufacture and are cheaper. Metal-based and film-type resistors are a little bit more expensive. These are typically used for applications requiring less noise, better thermal stability, and those that works better at higher temperatures and higher frequencies. Resistors can be described by their tolerances, the temperature coefficient, the operating temperature, the range of resistances, power rating, and the range of voltages. Carbon-based resistors offer the least performance characteristics and are only able to perform at relatively low current and temperatures. The metal film resistors are much better, but are more expensive. Here are a few more examples of carbon type and metal film type resistors and what they look in the inside. The resistances of carbon type resistors are determined by the ratio of carbon to ceramic materials. The more carbon is present, the lower the resistance of the resistor. Metal films, on the other hand, get their resistances from the degree of oxidation of the metal or from the spiral helix groove engraved on the deposited metal on a wire. The more oxide material is present, then the more resistive the material is. And if there are more spirals, the path for the charges to pass through is longer and the charges encounter more resistance. In some designs, the metal is wound spirally around an aluminum core. The aluminum wire helps in the dissipation of heat. Depending on the design of the resistor, you can apply power from as low as 1/8 of a watt to as much as 10 watts. This is important when designing electrical circuits. Hobbyists typically employ 1/4 watt resistor types and is sufficient for their purposes. You'll notice that as the power requirement increases, so does the size of the resistor. The reason for this is to reduce heat dissipation to allow more paths for charges to go through. If you don't have an ohmmeter or a multimeter to measure the resistance, you can determine it through the colors seen on the surface of the resistor. There are a few variations, but the most common is the resistor with 3 bands to the left and 1 band to the right. In any variation, the last band to the left of the right bands correspond to the multiplier or the power of 10, while the remaining bands are the digits. The tolerance corresponds to the level of accuracy of the resistance of the resistor. One type of resistive device is a potentiometer. A potentiometer is a resistor with variable resistance. A typical potentiometer has 3 leads or terminals, which you can see in the figure. The leads, labeled A and B, will give you a constant value of the resistance. This resistance value is the one that you tell the seller of electrical parts to give you. A typical value is 2 kiloohms. The resistance varies at terminals A and W and at terminals W and B, depending on how the shaft is turned. If you turn the shaft all the way such that the wiper is aligned with terminal A, then the resistance between A and W is about 0 ohms, while the resistance between W and B should be the same resistance as measured between terminals A and B. Conversely, if you turn the shaft all the way such that the wiper is aligned with terminal B, then the resistance between A and W is the resistance as measured between terminals A and B, while the resistance between W and B should be 0 ohms. If the shaft is turned such that the wiper is anywhere between A and B, there should be some finite value of resistance less than the resistance between terminals A and B. The sum of the resistances between A and W and B is the same as the resistance between terminals A and B, which should be quite obvious. Here are other variations of potentiometers. The variations in the dimensions depend on the resistances and the required application. These types of potentiometers are typically used if a person would like to change something in their electrical equipment or device. You'll most definitely find potentiometers in old television sets, for example, or in electrical fans. Turning the knob of an old television set changes its volume or the channel. In an electric fan, the speed of the blade changes as you rotate the switch. You'll get to know more about these potentiometers in our laboratory classes. Trimmers and dimmers are special kind of potentiometers. They are not used directly as an interface to change the volume or channel or fan speed, as in the case of potentiometers. These are typically used in devices for calibration and adjustment. Once you set the trimmer or dimmer at a particular setting, you almost never change that setting for a very long time. This reduces the need to remove an old resistor and replace and resolder with a new one. These are the standard values of resistors. You can never buy or find any resistance between these values. Resistors can be placed in series or in parallel as shown. When resistors are placed in series, the same amount of current passes through each of them. Thus, in a series connection, all resistances add up and the total or equivalent resistance is just the algebraic sum of the series resistances. When the resistors are placed in parallel, the current is divided at one junction, then adds up at another junction. In this case, the current adds up and the equivalent resistance is determined by taking the reciprocal of the sum of the reciprocal resistances. The total power is simply additive regardless of the type of connection. Capacitors are electrical components whose main purpose is to store electrical energy. This is achieved through charge separation, ideally placing the positive charges in one metal plate while the negative charges in the other metal plate. To prevent charge combination, a dielectric is typically used. To increase the surface area, the metal is rolled up such as that shown in the figures, and you can also see various types of capacitors based on the dielectric material used. These can be polyester, ceramic, or electrolytic, and the variation depends on the required application. The table shows the various characteristics of the different capacitors. The commonly used capacitors are electrolytic, ceramic, and mica. Electrolytic capacitors are polar capacitors. This means that they are designed to have a specific polarity and must be connected properly. On the other hand, the other types of capacitors are nonpolar and may be used without thinking about positive or negative terminals. Here are the typical capacitor values that you can acquire from electronics shops from a picofarad to about 10 millifarad. You will not be able to find any capacitor values between these values. Capacitors store energy by separating the positive charges from the negative charges. The separation is achieved by having the positive charges on one metal plate and the negative charges on another metal plate, and preventing them from recombining by placing a dielectric material between the metal plates. The separation creates an electric field. On each of the metal plates, the surface charge density is given by the electric field divided by the area of one of the metal plates. Due to the presence of an electric field, there exists an electric potential energy between the plates. In a related manner, when a person jumps, that person is separated momentarily from the earth and therefore creates a gravitational potential energy between the person and the earth. The electric potential energy per unit charge is what we commonly refer to as the voltage. The capacitance of the capacitor is therefore is defined as the charge per unit potential. To better understand this, you can ask yourself, how much charge is needed to create an electric potential of 1 volt? The more charge is needed, the greater the capacitance. The total energy stored in a capacitor is then related to the capacitance as shown in the last set of given equations. Capacitors can be arranged in series or in parallel. Each capacitor in series has a specific voltage. Since voltages in series are additive, then the equivalent capacitance of a series capacitor circuit is computed from the reciprocal of the sum of the reciprocal capacitances. This is easily derived through the inverse relation of the capacitance and the voltage of a capacitor, and thinking that the charges in each of the capacitors is the same for all capacitors in series. This is true because the current is the same for all capacitors in series. For capacitors in parallel, the current divides at a junction and then adds up again in another junction. Thus, the total current is just the sum of the individual currents through each capacitor. Equivalently, the total charge is the sum of the individual charges on each capacitor. Since the capacitance is proportional to the charge, the equivalent capacitance of the capacitors in parallel is just the algebraic sum of the individual capacitances. An inductor is an electrical component that stores magnetic potential energy. It is a very simple device made by simply coiling a metal wire such as a copper wire. The magnetic inductance describes the ability of an inductor to resist any changes in current passing through the inductor. Thus, an electromagnetic force, or commonly referred to as the inductor voltage, is generated whenever there is a change in the current. The product of the inductance and the current is called the magnetic flux. The magnetic flux describes the magnetic field passing through a unit area. Thus, if the magnetic flux changes, an EMF or a voltage is generated across the inductor. It is during that time when a voltage is generated that the magnetic potential energy is stored. It should come as no surprise that some inductors that you can buy look like resistors. As we've mentioned before, some types of resistors are manufactured by winding metal. For such types of inductors, a color guide is also used to determine the inductance. The color assignments are basically the same as that for resistors, except that the multiplier is in units of microhenry. The standard inductor values that you can acquire from some shops are listed in the table. For inductors in series, the equivalent inductance is just the sum of the individual inductances, since the voltage across the inductor is proportional to the inductance. In parallel inductors, the equivalent inductance is just the reciprocal of the sum of the reciprocal inductances. The energy stored in an inductor is proportional to the inductance and the square of the current through the inductor. I hope that this video has allowed you to recall the concepts that you learned from Fundamental Physics 2 or Physics 102. We will be using these concepts over and over again during this course. We'll particularly be taking a look at the response of these electrical components to an AC source. See you again in the next lesson!